When we're solving first-order differential equations, how we attack the problem has to do with what form the problem is in. We've already learned how to do two different types. We've done separable first-order differential equations. That is when we can put the independent variable on one side of the equation and the dependent variable on the other. For instance, a differential equation such as this is separable because if I rearrange things, I can get the dependent variable y on the left-hand side and the independent variable x on the right-hand side. And to solve this, all I would do would be integrate both sides. We also learned how to handle linear equations. That is, equations that can be put into the form dy dx plus some function of x times y equals another function of x. To solve this, we use the integration factor, which is found by mu of x equals e to the integral px dx. And we'd set the differential equation up like so, and then solve. There are also differential equations that are exact. That is another particular form that the differential equation is in. But we're going to start talking today about substitutions, and our first substitution method is going to be the homogeneous substitution. This can also be pronounced homogeneous. However, later in the course we're going to be using this very same word in a completely different method. So to kind of keep track of those, when I use them for the substitution, I'm going to pronounce it as homogeneous. And later on in the course, when I use it to solve second-order differential equations, I'll be using the pronunciation homogeneous. Another type of substitution I'll be doing is the Bernoulli substitution. If we have a differential equation in the form dy dx equals a function of both x and y, we can use a homogeneous substitution if that function f of xy can be written solely in terms of the ratio y over x. Let's look at an example of this. This equation may not look like it can be written in the form y over x, but if we rearrange things a little bit, it can. And if we keep going, we get it down to the form where it's dy over dx equals y over x minus 1. On an exam, when I give you a homogeneous substitution question, I will be telling you it is in fact homogeneous. When I give you a question that is separable or linear, I might not tell you which method to use, but I will be telling you when to use the homogeneous substitution method. When I do so, even if it can be solved a different way, for credit on the exam, you have to solve it using the substitution method I've asked. So we've determined this one is homogeneous. Let's look at an example that isn't homogeneous. Here's such an equation. And if we rearrange things a little bit, I can get it down to this form. And if I go ahead and divide the numerator and denominator by 1 over x, wanting to get things in the form of y over x, let's see what happens. It's looking good, except for that 1 over x. It looks like I'm not going to be able to use the homogeneous substitution method for this problem. Also, keep in mind, on exams, if I ask you to use the homogeneous substitution, I don't try to trick students and give you a problem that actually isn't solvable with that particular substitution. So if you can't get it in the right form, it means you've made a mistake, and be very careful with your algebra. Alright, let's see how we could solve this homogeneous substitution problem. Substitution problems work a lot like the U substitutions that you used in Calc 2. What I'm going to do is say, let V equal that ratio of x over y. If that's the case, what is dv equal to? Well, I don't think this form is going to help me that much. So instead, I'm going to rewrite this v equals y over x as y equals v times x. Now, instead of trying to find dv, I'm going to focus on finding dy dx. Using the product rule, I'm going to get v times the derivative of x with respect to x plus x times the derivative of v with respect to x. When I do that, it simplifies to v times 1, or just v, plus x times the derivative of v with respect to x. Remember, v is a function of x, and the derivative of v is 1 times, by the chain rule, the derivative of v with respect to x. Let's go ahead and substitute this into our problem. We can rewrite y over x as v. Now let's do the same substitution for dy dx. dy dx is equal to v plus x times dv dx. And now what we're going to do is put this in the form dv over dx. First, we notice that there's a v on both sides of the equation, so we could subtract that away. And then we might notice that this looks like a separable equation. And this can be rewritten in the form of dv equals negative 1 over x dx. Well, I know how to solve separable equations. All I'll do is integrate both sides, and I'm done. Well, actually, I'm not done. If my original problem, which is up here, was in terms of y and x, I certainly don't want to leave things in terms of v. This is again just like in Calc 2, when you did a u substitution, you always had to translate it back into the x world. So let's go ahead and substitute for v, and let's put this in explicit form. And there we have our final answer. Let's do one more problem. So when we get a problem like this, the first thing we do is try to get things in terms of dy dx equals something. Let's go ahead and do that. There's our first step. Now we'll divide both sides by dx and x squared. And what we do for a lot of these problems is split up our fraction into separate terms. There's my first step, and now everything is in terms of y over x. Let's go ahead and do our substitution. What I'll give you on the exam is the substitution itself. I will give you v equals y over x, but that's it. So what you'll need to do is recreate what I just did. We first write y is equal to xv, then I take the derivative of both sides with respect to x, and I'll go ahead and use my substitution at this point. Always after this step, you will have things in terms of v and x. If you still have y's left over, that means you haven't done the substitution correctly. Now that I have things in terms of v's and x's, I'm going to go ahead and get this separated out. Again, there's a v on both sides that we can divide out, and it separates out to this. Now we're going to integrate both sides. The integration on the left-hand side is one you should recognize as the arctan. And then, of course, the natural log of x, and we can't forget that plus c. We substitute the v back, and then we're going to get this in explicit form by taking the tangent of both sides. And lastly, multiply both sides by x to get our answer. And there we have our final answer. Let's review what we've done. For homogeneous substitutions, the first thing that we do is get it in the form of y over x. Then, using the substitution v equals y over x, we go ahead and get that in the form of y equals x times v, and dy dx is equal to v plus x dv dx. That's using the product rule and the chain rule. These problems will always separate, and then we can solve them. All homogeneous substitutions turn into separable equations, which is something we know how to do. When we get to the Bernoulli substitution, that substitution will turn everything into a linear problem, which again we know how to solve.